Okay, I hope I'm audible and my screen is visible. And if possible, please confirm someone if all things are okay. Yeah, so this is today is okay. Thank you, Abhishek, confirming. And today is this is the extra tutorial session. This is the um, tutorial extra. Um, Advanced linear algebra, linear algebra, that is NOC 25 MA03, and today is 15th April, and this is the last tutorial session. Okay, so in today's class, I will mainly discuss some of the problems which is remains to solve in the last class, and as well as I will do some problems which are related to the quadratic forms. Okay, so first do some problems. I think we have done this problem. So let's do this problem. So what it says, given a linear operator t from a t x comma y equals to given by this way, and on the standard uh, given okay on the standard inner product space C2, then the corresponding Sesqui linear form, then the corresponding Sesqui linear form on V is given by this one. So which one is the sesquilinear form? So sesquilinear form means what is the definition? Definition of sesquilinear form, just a minute. Definition of sesquilinear form is the bilinear form which is linear in first coordinate and antilinear in second coordinate. Antilinear means conjugate linear. Okay. So we'll check whether which one is the bilinear form, which one is the sesquilinear form. Just a minute. So So here f is given by this way. So um, let's take first one. Whether first one is correct or not. Okay. What are the answer? I have to get those things as well. So let's first check first one. First one is given that option A is giving that f of x1 y1 comma x2 y2 is equals to a bar x1 x2 bar comma b bar y1 y1 x2 bar plus c bar x1 y2 bar plus d bar y1 y2 bar. Okay, so you can look at here we have this coefficients at the bar also, right? So no problem. So let's try. Let's take three element x1 y1 and another is x3 y3 and another is x2 y2 is belongs to and some constant term gamma, constant term gamma, this all are belongs to the vector space, that is the V, and let gamma is a constant in complex number C. Then what it is that x1 comma y1 C gamma of x1 comma y1 plus x3 comma y3 comma x2 comma y2, what it will be, it will be equals to uh, okay, okay. So this is equals to, it will be AF of gamma x1 plus x3 comma gamma y1 plus y3 comma x2 comma y2. x2 comma y2. So this by definition it will be equals to a1. This is now new x1. This is now new x1. This will be now new x1. This will be now new y1, and this is as usual x2, y2. So this is so now a bar. Now in place of x1, I will replace x1 x1 plus, in place of x1 I will replace gamma x1 plus x3, and in place of x2 I will replace x2 is there, x2 is as it is, plus b bar into y1, b bar into y1, b bar into um, y1. What is y1? Y1 is now gamma y1 plus y3, that is in bracket, plus into x2 bar plus c bar x1 is gamma x1 plus x3. Okay, so this one into y2 bar is y2 bar plus d bar y1 y2 bar. Okay, what is y1 y2 bar? Y1 y2 bar, what is y1 y2 bar? Y1 is this one, so gamma y1 plus y3 into y2. Okay, so now if I can break it, what I'll get that a1, so I can take gamma common, and it will be if I just take this term, what it will be, a bar x1 x2, that is the first term, x2 bar it was, x2 bar plus b bar y1 x2 bar, this term with this, and last one this term is plus c bar x1 y2 bar plus d bar y1 y2, this one is there, plus a bar x3 x2 bar plus b bar y3 x2 bar plus c bar x3 y2 bar plus d bar y3 y2. I think y3 y2 bar was there, right? So this will be bar. This will be bar. So therefore one can look at, this is actually f of x1 comma x2 comma y1 comma y2 plus, this is actually the second term is, this will be actually f of x3 y3 comma x2 y2, right? So therefore this is linear, so therefore f is linear in first variable. So what we have to check is now that whether it is conjugate linear or not. So similarly, what I will consider, let f is bracket f into there. So this will be, alpha will be replaced by x1 y1 comma gamma x3 plus y3 whole into x3 comma y3 plus x2 comma y2, right? I will have this one. So what it will be, f of x1 comma y1 comma gamma x3 plus x2 comma gamma y3 plus y2. Okay, this one. So therefore one can write this one this way, f of x1 comma gamma, okay, x1 minus gamma x3 minus x2, sorry, not minus, what is it is, okay, so I have to now use, this one is now new x2 and this one is now new y2. So now I have to use the formula, what it says, formula is says, I have to take the look from the formula, what it says, a bar x1, that will be a bar by formula x1 into x2 bar. X2 bar is gamma y3 plus y2 bar plus b bar x1 into y2 bar. Y2 bar is, so this is x3 bar, sorry, x2 bar. So x2 bar is new, x2 bar is x3 comma x2. B bar x1 y2 bar. Y2 bar is gamma y3 plus y2. Okay, this one with bar plus d x3 y2 bar Oh, sorry. Actually, I'm doing some little wrong. What is the question? Given the linear operator t from this way, the standard inner product, then the corresponding linear. Okay, corresponding linear. Okay, sorry. Very sorry. This is not the things actually. We have to do the for all of them are actually sesquilinear form, but we have to do it. We have to find the sesquilinear form um, for the operator t. Okay, sorry, I miss. Sorry, actually, I misread the questions. So that's why answer is not going. Answer is becoming too long. Okay. So here first I will give the what is the corresponding linear operator. Okay. Let say some theorem. Let V be a finite dimensional inner product space and if A form on V, then the form then inner space on finite inner space and T from V to V be a linear operator, then corresponding sesquilinear form is given by f alpha comma beta is equals to t alpha comma beta for all alpha comma beta is coming from the vector space V. So therefore here it is given that t in this case t from V to V is given by t of x comma y. T of x comma y is equals to ax plus by comma cy plus dy, cx plus dy, cx plus dy, right? I believe I have written x plus by, cx plus dy. Then corresponding linear form, corresponding sesquilinear form, corresponding sesquilinear form is given by f of x and y. Sorry, corresponding sesquilinear form, that means two element will be there, that is x1 comma y1 comma x2 comma y2, that should be equals to t of x1 comma y1 with inner product x2 comma y2. Okay, so this is equals to ax1 plus by1 comma acx1 plus dy1, right? Ax1 plus by1, cx1 plus dy1. This is the element with inner product x2 comma y2. This is the thing. Okay. So here it will be ax1 plus by1 whole into x2 bar plus cx1 plus dy1 whole into y2 bar. This is the standard inner product. Recalling the standard inner product of C2. Recalling the standard inner product of C2. Okay. Now what I will get, this can be written, this can be expand ax1 x2 bar plus by1 x2 bar plus cx1 y2 bar plus dy1 y2 bar. So therefore, what is the option, correct option? You can look at this is the only correct option. X1, no, just a minute. X1 x2 bar y1 x2 bar, yeah, x1 y2 bar y1 y2 bar, yeah, this is only correct option, so all other options are automatically false here. Okay, so what one thing I can write here is that if a sesquilinear form f is given on a finite dimensional inner product space V, then the matrix then if let alpha 1 all the way alpha n be an orthonormal basis of V, because V is an finite dimensional inner product space, it must have an orthonormal basis, and F is a Sesqui linear form on V. Then matrix representation of F is given by, that is called TF that is equals to TF matrix representation. It at the point I comma j, that is equals to inner product of, so that is equals to f of alpha j comma alpha I. This is the corresponding matrix representation. Yeah, yeah, this is correct. So if the matrix representation, if I write it like a of f at the point I comma j, this will be f of alpha j comma alpha I. So therefore, if we consider this is a for all I and j coming running over 1 and 2, for all for all for all 1 less than equals to I, j less than equals to n. So that is, if we take this is a matrix, suppose we are given a Sesqui linear form F on a finite dimensional linear product space V, then in that situation we can get a matrix A F which ij entry is given by this way, because F is known now. So in that situation this will be a matrix. So and after that the F of alpha beta, that will be equals to F of A, sorry, that will be equals to inner product of A alpha comma beta for all alpha and beta is coming from the vector space V, and A is the matrix AF IJ. This is the matrix. So that means there is a correspondence. Basically, if for a fixed orthonormal basis, there is a correspondence. Okay. So let's go to the next problem. With this one we have done now. This is the another problem. So what it says, given an inner product space V equals to R3 equal to the standard inner product on R3, real inner product, and linear operator T from V to V defined by this way, in the resolution of identity operator E1, E2, E3 defined by, okay, so first that is something we have to do, okay, that is some resolution operator means we have to find many things actually, we have to find many things, okay, so let's do step by step I think. So we'll first find the matrix representation of P, and then we have to find the eigenvalues, and we have to find, okay, so first find the eigenvalues of the matrix representation of T with respect to the standard order basis. So matrix representation of T is given by 4 minus 1 minus 1, okay, sorry, this is in reverse way, 4 minus 1 minus 1 minus 1 minus 1 4 and minus 1 4 minus 1. This is the matrix representation. So now You can look at this symmetry, that doesn't matter. Okay, then a minus is a equals to this, then a minus lambda I is 3, that will be 4 minus lambda minus 1 minus 1 minus 1 minus 1 4 minus 1 minus lambda minus 1 4 minus 1 minus lambda. This is the matrix. So therefore what I will get, this will be equals to, we have to first do some row reduction, that will be easy, but we can directly also go, that is not a problem. But we can make easy, we can at least remove 2 row. Okay, so we'll do column operation. So let's do the column operation. Because you know the after row reduction the matrix will not change. 4 minus lambda, we will subtract row column 3, column 2, sorry column 3 is equals to column 2 minus column, sorry column 3 minus column 2. So what we'll get, we can do, that is same with row operation, that is not a problem. Or we can do the row operation as well. Okay, so do the let's find directly. No need to go any row operation, column operation. So this will be equals to 4 minus lambda into determinant of minus 1 minus lambda 4 4 1 minus lambda, right? Minus 1 minus 1 1. This will be minus into minus 1 plus 1. It will be minus 1 4 minus 1 minus 1 minus lambda, and this will be minus into, because this one will be negative, minus 1 minus 1 minus lambda minus 1 4 4. So therefore what it will be, 4 minus lambda into 1 minus lambda 1 plus lambda 1 minus lambda square minus solo this one plus this will be 1 plus lambda plus 4 minus this will be minus 4 minus 1 minus lambda. I hope I have written correctly. So therefore it is 4 minus lambda into minus lambda square minus 15 plus lambda plus 5, it is plus lambda plus lambda plus 5. Yeah, so that means we can write it as 2 lambda plus 5, that way. So therefore what will be the corresponding characteristics polynomial, that will be, or we can do the diagonalization process, that will also help. So here it will be 4 minus 4 lambda square minus 60 minus lambda cube minus 4 lambda square minus 60 minus lambda cube minus lambda minus 4 lambda square minus 60 plus lambda cube plus 15 lambda, this one plus 2 into lambda plus 5. So I hope lambda plus lambda equals to 5 will be minus 5 will be a solution. So let's write it as that form, that lambda cube lambda minus 5 lambda minus 5 lambda minus 5 lambda square lambda cube minus 5 lambda square plus lambda square minus 5 lambda minus 20 20 no 20, this will be okay, lambda cube, if I want to plus lambda, take lambda square minus 5 lambda. Now I want to do it is 20 this will be 100 then. Okay, why I'm doing this way, so this is the thing, we have this one. So let's completely break it. This will be lambda cube minus 4 lambda square plus 17 lambda, this is 10 minus 50. Okay, so this is, I am writing that lambda minus 5 lambda minus 5 lambda minus 5 or lambda minus 2. 2 will also be a solution. So if you replace 2 here, what you will get? Replace lambda by 2, what you will get? That 8 minus 60, 16 plus 34 minus 50, what you will get? Uh, 8 minus 4, 4, 16, 7 to 34 minus 50. Okay, just a minute. I think I have made some mistake. Just please give me some time. 4 minus lambda, 1 minus lambda, 4, 4, 1 minus lambda. That's okay. Here is a mistake. I have doubt that I made a mistake. So this will be 1 plus 2 lambda plus lambda square. So this will be lambda square plus 2 lambda minus 15. Okay. So then this all equation will change. This will be 4 lambda square plus 8 lambda minus. Okay, so I can break it here. 4 minus lambda, I can write it lambda square plus 5 lambda minus 3 lambda minus 15 plus 2 into lambda plus 5. So I don't need to go then that way. So what we'll get here, that will equals to 4 minus lambda into lambda plus 5 into lambda minus 3 plus 2 into lambda plus 5. So therefore it will be lambda plus 5 will be common, and this will be 4 lambda minus 12 minus lambda square plus 3 lambda plus 2 lambda plus 10, that is equals to lambda plus 5 minus lambda square plus 7 lambda, or I can take minus lambda outside, lambda square plus 9 lambda, 9 lambda, 3, 2, 4, 7, 9, and minus 12 plus 10, that is plus 2. Okay, God, what is that? This is more absurd. 4 lambda, okay. Okay. This is the value. This is 2. This is then 7 lambda minus 10. So 5 2 minus lambda plus 5, it will be lambda minus 5, lambda minus 2. So therefore lambda equals to plus 5 minus 5 to our eigenvalues. Okay, these are the eigenvalues. So when we get the eigenvalues, so therefore the corresponding, if you recall, in one problem we have written the corresponding, this is diagonalizable, that implies that t is diagonalizable as characteristics polynomial is itself minimal polynomial minimal polynomial, and that is completely factorized into distinct product of distinct factors, and that is completely factorized that completely factorized into distinct linear factor. Therefore, it is diagonalizable. Okay. So as this is diagonalizable, so so there must be there must be mm, so then we know that then T is equals to summation of Ci I equals to 1 to 3, where C1, C2, C3 are distinct eigenvalues and EI are orthogonal projection of V onto the eigenspace of Ci. So, but then we know this EI is equals to if I consider a polynomial, EI is equals to PIT for some polynomial Pi, where Pi is actually Lagrange's polynomial. What was that? If I want to find Pi, then it will be J not equals to identity, and J will be run from 1 to whatever the value, that x minus Cj by Ci minus Cj. So that is in this situation. So therefore, P1 will be x minus C2 by C1 minus C2 into x minus C3 by C1 minus C3, that is equals to this is equals to, so C1 C2, here C1 is equals to, let's take 5, C2 is equals to minus 5, and C3 is equals to 2. So therefore, what we'll have, this is equals to, we should have C1 equals to 5 and this one, so x minus 5, that is x plus 5 into x minus 2 by C1 minus C2, that is 10, into C1 minus C3, that is equals to 3, that is equals to 1 by 30, into x minus 2 into x plus 5. So we know what it is now. So therefore, E1 is equals to P1 of T, that is equals to 1 by 30 of T minus 2 times identity into T plus 5 times identity. This is the thing, right? Or in this, with respect to matrix representation, it will be, what was the matrix, that is 4 minus 1 minus 1 minus 1 minus 1. So 4 minus 1 minus 1 minus 1 minus 1, and this is minus 1 4 4 minus 1 minus 1 4 4 minus 1 minus 1 4 4 minus 1, this one minus, okay, so I have to write this is a little carefully, this one minus 2 times identity, so 2 minus 1 minus 1 minus 1 minus 3, 4 minus 1 4 minus 3, this one is the first matrix. Another matrix is the sum of 5, 9 minus 1 minus 1 minus 1 4 4 minus 1 4 4, this is the matrix. So if I multiply, what it will be, it will be 1 by 30, 2 9, I think it is, what will be to 9 18 18 plus 2, that is 20, and next is that, Okay. Next is that that 2 minus 4 minus 4 minus 8, that is minus 6. No, this one with this minus 2 minus 4 minus 4 minus 10. Next one is that 2 minus 2 minus 4 minus 4 minus 10. Next one is that minus 1 minus 9 plus 3 minus 4 minus 10. Next one is that um, next one is that minus 1 minus 12 plus 16, that is 4 minus 1, that is minus 5. Next one is that 1 minus 12 plus 16, 1 minus 12 plus 16, that will be 5 again, 5. And I think the second one is 1 minus 12 plus 16, that is again 5. Next one is that minus 9 minus 4 minus 13 plus 3, that is minus 10. That is second one is that 1 minus 16 minus 15 minus 15 minus 12. It's a 1 plus 16, 17, 17 plus 12 minus 12, that is 15. Sorry, that is 5. 5. Next one is that 1 plus 16 minus 12, that is 5 again. So this is the matrix, so that will be cancel out, or you have to do all cancel out, and it will be 4 minus 2 minus 2 minus 2 1 1 minus 2 1 1. So this is the projection 1. Okay, so now projection, what is the, and so therefore E1 of x y z, that is equals to 1 by 6 4x minus 2y minus 2z minus 2x plus y. So that will be, so that will be 4x minus 2y minus 2z comma minus 2x plus y plus z minus 2x plus y plus z. So let's check whether which of the option is there which is satisfying this condition, minus 2x plus y plus z. So all the option is there. Minus 2x minus 2 4x minus 2y minus 2z, 4x minus 2y minus 2z minus 2x plus 2yz. This is the, okay, so this is actually, so all other option is there, so I have to go to the for other one. So other one is that, let's take E2. E2 is equals to corresponding to I have written E1 corresponding to plus 5. So E2 is corresponding to P2 of ID, and where what is the P2? P2 of Jx is equals to x minus 5 by minus 5 into x minus 2 by minus 5 minus 2. Okay, so therefore it will be minus 10 into 7, 1 by 70 into x minus 5 into minus 10 minus 7, 17, x minus 5 x minus 2. So therefore that will be 1 by 70 into, that will be 1 by 17 into t, what was that, that this one is the t matrix, that 4, that will be the, that one matrix. If we subtract it from that matrix, what was the matrix representation, what I will get, I have to subtract it from the matrix representation, I have to subtract 5 identity. So therefore it will be minus 1 minus 1 minus 1 minus 1 minus 1 minus 5 minus 6, and it will be minus 4, it will be minus 1 4 minus 6. Okay, this one with 2 will subtract, and 2, if it is 2 subtracted, then it will be 2 times identity this matrix, 2 minus 1 minus 1 2 minus 1 minus 1 and minus 1 minus 3 4 minus 4 minus 1 minus 3 4, and next is minus 1 4 and minus 3. Okay, this is the thing. So if I multiply it, what it will be, first one will be minus 2 plus 1, that is 0. Second term is 1 plus 3 4 minus 4 0. Third term is 1 minus 4 plus 3, that is again 0. 1 minus 4 plus, that is again 0. Okay, next one is that minus 1 minus 2 plus 6 plus 4, that is uh, minus 2 plus 6 plus 4. So that is 8. Yep. And if I subtract 2 times identity, 2 minus 1 minus 2, that's true. So if I multiply it, this one with first term, minus 2, minus 2 plus 6 plus 4, that is equals to 8. I hope I am writing correctly. Mm, this is the mistake I'm making. This is the mistake I'm making, right? So this will be minus, this will be minus 0. So therefore this is 0. This is 0. So next one is that minus 1, middle one, that is 1 plus 18 plus 16, that will be 17 plus 18, that is 35. Next one is that 1 minus 24 minus 12, that is equals to minus 35. Minus 35. Next one is that minus 2 minus 4 plus 6, that is 0. Next one is that 1 minus 12 plus 24, that is okay, 1 minus 12 minus 24, that is equals to minus 35. Next one is that 1 plus 16 plus 18, that is again 35. So this is 35. So what it will be? It will be equals to, it will be equals to 0 0 0 0 1 half, actually minus half, or I can write half outside. Half 1 minus 1 minus 1 1 0. So therefore what I will get, then P2 of P2 of then what will get, P2 of A is there. So P2 of T, that with the element x y z, it will be 0 first one, this one is 0, this one is 0. Next one with this will be y minus z, and next one will be minus y plus z, all with half. So y minus z minus y z. Let's check whether which one is that. Y minus z minus y z. So these two are the options. So you have to check the last one to confirm. So you have to check the last one as well. So then, and E3, that is equals to P3T, where P3Jx is equals to C3, sorry, x minus x1, x minus c1 whole into x minus c2 by c3 minus c1 into c3 minus c2. Recall that c1 is equals to 5, c2 equals to minus 5, and c3 is equals to 2. So therefore what I will get here, so C1, x minus C1 is there, C3 minus C1 is minus 3, and C3 minus C2 is 7. So 1 by 21, x minus C1, that is 5, and x minus C2, that is 2. So therefore PE3 is equals to 1 by 21. That matrix was, I am just writing for the sake of to make it easy. The matrix was 4 minus 1 minus 1 minus 1 minus 1 4 minus 1 4 minus 1. So this will be 4 minus 5, that is minus 1, next one is minus 1, next one minus 1, minus 6, 4, minus 1, 4, minus 6, another one is the 2, minus 1, oh, C1, C2, that is 5, okay, C3, that is 2, minus 5, that is minus 3, 2 minus 5 is minus 3, and 2 plus 7, so that will be minus, so this will be, oh sorry, one will be plus, this is plus, so plus 9, minus 1, minus 1, minus 1, minus, that is 4, that is 4 again, minus 1, 4, that is 4, so what will get, this will be minus 1 by 21, first will be minus 9 plus 1, that is minus 7, next will be, I am removing this matrix, next will be 1 minus 4, that is again minus 7, next will be 1 minus 4, that is minus 7, next will be minus 9 plus 6 minus 4, that will be 13, that is again minus 7, next will be plus 1 minus 24 plus 16, that is again minus 7, next one is 1 minus 24 plus 16, that will be minus 7, next one is minus 9 plus 4 plus 6, oh, minus 9 minus 4 plus 6, so 13, that is again minus 7, next one is 1 plus 16 minus 24, 1 plus 16 minus 24, 17 minus 4, that is minus 7, 1 plus 16 minus 24, that is minus 7. So 1 by 3, 1, 1, 1, 1, 1, 1, 1, 1, 1. So this is the matrix. So therefore, what we will get? So E3 of x, y, z, that will be 1 by 3 minus x, sorry, x plus y plus z, comma x plus y plus z, comma x plus y plus z. So this is the thing. So let's go to the options. Mm, First two options was there, and all are plus. So therefore this is the correct one. So this is correct and all other automatically becoming false. So this one is a long problem. Oh, sorry. Y minus z. Sorry. I made a mistake. In what was the E2? E2 is E1. What was the E2? It is y minus z minus y plus z. Y minus z minus y plus z. Just a minute. Yes, B is the correct option. I have the correct. This is correct. This is correct. There is no problem. So B is the correct options. All other options will be incorrect. I hope it is clear. Now I will go one more two problems and then I will go some other problem. So B is correct option. So this is also same way, but I will not do because first you have to find the t square and then we have to do the similar thing. Yeah. So no, this will be done. Just let me do a little bit. Okay. This will be done by the previous one. So what it says, given an inner product space V equals to R3, given an inner product space V equals to R3, Q to the standard inner product on R3 and linear operator T from V to V defined by this way. Tx, y, z is equals to 4x minus y minus z, comma minus x minus y plus 4z, comma minus x plus 4y minus z. This is the txy. So therefore, what I will get t square x y z is equals to 4 into, this is now new x, this is now our new x, this is now our new y, this is now our new z. So 4 into 4 into, so 4 into x is 4x minus y minus z minus y is the this one, y is minus x minus y plus 4z, and z is minus of minus x plus 4y minus z, comma uh, y is minus x minus 4x minus y minus z minus y is minus x minus y plus 4z plus 4 into z is minus x plus 4y minus z, and comma, and z is minus x 4x minus y minus y minus z, and plus 4 into y is minus x minus y plus 4z minus z into z x minus 4x 4y minus z. This one will give 16x minus 4y minus 4z plus x plus y minus 4z plus x plus minus 4y plus z, comma minus 4x plus y, or you can directly, let's sum the coefficient of this is minus 4 plus 1 minus 4 minus 7 minus 4 plus 1 minus 4 minus 7 x plus 1 plus 1 2 plus 4y 16y, that is 18y plus z minus 4z, that is minus 3z minus 4z, that is minus z. Okay, next one is okay, so this is a similar process it will be, but it is too long, so I'm thinking whether should I do or not. Oh, sorry, I should not. I'm just doing something very absurd. We have seen that when t of x y z is equals to 4x minus y minus z, comma minus x minus y plus 4z, comma minus x plus 4y minus z. In that situation, the spectral set is the, we have seen the spectral set when t equals to this. We have seen the spectral resolution when t equals to this, and that is P equals to C1 E1 plus C2 E2 plus C3 E3. Recall that this EI orthogonal projections. Recall that CEI are orthogonal projections. EI are orthogonal projection. That means they are orthogonal with respect to each other. That means their range is orthogonal. So therefore that c square is equals to c1 square e1 and this ei. So basically that is, and basically it is saying that ei ej is equals to ei again if I equals to j, 0 if I not equals to j, and c2 square e2 plus c3 square e3. So there it will be, we know what is the c1. C1 is equals to 5, c2 is equals to minus 5, and c3 is equals to 2. So therefore it will be 25 E1 plus 25 E2 plus 4 E3, and we have seen what is E1, E2, E3. So in that term, if we go, so the coefficient will only change, and that will be, I think this one is the, what was the second last option, that is y minus z minus y plus z, y minus z minus y plus z. Just coefficient will only be the factor. So this one is the only option, because this is the correct option there we have getting. This will be the correct options. Then from the solution of the last problem, solution of the last problem, we get that option D is correct. Okay. So I think we have done this in the last class, so I will not go this one. This is the last problem. I think this is visible. So what was the problem here? Here it is said that the A be the singular value decomposition. We have to find the singular value decomposition. Question is this, that we have to find the singular value decomposition. This is the question. So A is given 3, 2, 2, 2, 3, minus 2, and the singular value decomposition of A is given by UV, UDV, where U and V are the orthogonal matrices of order 2 and 3. So what is the general procedure of the singular value decomposition? So as we know, singular value decomposition, singular singular value decomposition. What that says? That says let A be a matrix of order m by n over the field complex field. Let's say then there exists unitary matrix U of order m by n and V of order n by n such that UAV is equals to UAV is the diagonal matrix, is a diagonal matrix is a diagonal matrix, and this is called, and this existence of U, and this decomposition of this decomposition is called, okay, sorry. Okay, so UV you have to find. So okay, let's find UV and then we'll find U star UV, that will be done. So first of all, what was the in general procedure for to finding the decomposition? So first we have to write what was A. A is 3 2 2 2 3 minus 2. 3 2 2 2 3 minus 2. I hope I've written 3 2 2 2 3 minus 2. Uh, this one, and A star A is equals to 3 2 2 2 3 minus 2. This is 2 by 3, and this is 3 3 by 2. 3 2 2 2 3 minus 2. So what will get? 6 plus 9 plus 4, that is 13, and 6 plus 6 12. 6 minus 4 2. 6 plus 6 12. 4 plus 9 13. 4 minus 6 minus 2. 6 minus 4 2. It will be minus 2. 4 minus 6, that will be minus 2, and 4 plus 4 8. So this is the A star A. Okay. Now you know that A star A is positive definite. So that means A star A positive definite. That means that is A star A or any vector x with inner product x, that is always greater than equals to 0, because this is becoming ax comma ax, and that is actually norm of ax square. That's why it is saying that A star A is positive definite. So when A star A is positive definite, it must have it should have a diagonalization. So there exists an unitary operator V of order 3 by 3 such that V star A star A V is equals to diagonal of the identity, diagonal of the diagonalization, diagonal matrix of some particular eigenvalues. Okay. So what are the eigenvalues? First we have to find diagonal of lambda 1 square, lambda 2 square, and all this. Where lambda 1 square, lambda 2 square, all the way are eigenvalues of A star A. Note that here we are writing the eigenvalues of A star A by lambda 1 square, lambda 2 square, because A star A is positive and self-adjoint. Therefore, all the eigenvalues of A star A uh, positive, will be positive real number. So therefore, it will be something like lambda 1 square for some lambda. So let's find the eigenvalues of A star A. What was the A star A? Was 13, 12, 2. So 13 minus, so one can write as A star, and you can, if you write this is as a B, so B minus lambda identity, that is equals to 13 minus lambda comma B, 12, 2, 12, 13 minus lambda minus 2, 2 minus 2, 8 minus lambda. So this is the matrix. So what we'll get? We'll get here, how to calculate all this eigenvalue. So we have to calculate all the eigenvalues. So therefore, what it will be? It is 13 minus lambda. I think if we do the, let's do it. 13 minus, that is 13 minus lambda minus 2 8 minus lambda minus 12 12 minus 2 2 8 minus lambda plus 2, that is 12 13 minus lambda 2 minus 2. So therefore what we'll get, that is equals to 13 minus lambda into oh god, that is big matrix. This is correct. Let's do it. 8, 8, 8, 1044 minus uh, just a minute. This will be plus lambda square minus 13 lambda minus 18 lambda 8 lambda, that is 21 lambda, plus this one minus 4 minus 12 into this will be 96 minus 12 lambda plus 4, this will be 2 into minus 24 minus 26 minus 2 lambda, right? So therefore what it will be, that will be 13 minus lambda into lambda square minus 21 lambda plus 100 minus 12 into plus 12, 12 lambda plus minus 100, and this will be plus minus into minus 2 into 2 into 2 lambda plus 50. Am I written correctly? Minus 24 minus 26 plus, this is plus 21. So therefore this minus can not be taken. So this will be 2 into 2 lambda minus 100. Okay. So therefore what I will be getting here, so that is 13 lambda square minus 3, 6, 26, 27 lambda plus minus lambda cube plus 21 lambda square. I think better to, whether I'm doing anything wrong. To get the diagonal at least. Okay, let's go ahead. So this is 13 lambda minus 273, 13, 3, 1, 26, 27 lambda plus 1300 minus lambda cube plus 21 lambda square minus 100 lambda plus 144 lambda minus 1200 plus 4 lambda minus 200. So therefore what will get, minus lambda cube 13 lambda square 21 lambda square plus 20 34 lambda square. And next is 100 lambda 144 lambda 4 lambda and 273 lambda. So if I just sum them all, so what I'll get, uh, what I'll get, calculation, but what is the calculator here? So that is minus 273 plus, no, minus 273 minus 100 plus 4. Very odd numbers are getting. Oh, sorry. Minus 273 minus 100 plus actual 144 plus 4, 225, 225 lambda and 4 lambda 144, this one and this one. So the 1300 minus 200, that is minus 100. That is, so what we'll get, the equation is lambda cube minus 34 lambda square plus 2 to 5 lambda plus 100. This is equals to 0. So I just want to check whether the case is correct or not. 26, yeah, this is correct. There is no problem with this. So therefore, whether we have to check whether lambda equals to 1 is a solution. 1 minus 34 plus 2 to 5 plus 100, that will definitely not be the solution. Minus 1 is also not be the solution. So let's write lambda equals to 2. So that will be 8 minus 4, 4, 6. If I just replace lambda equals to 2, then 8 minus 34 into 4 plus 2 to 5 into 2 plus 100. I think this 100 numbers is correct. 1200, this is 100 minus this is 100. This is correct. 1300, 1200, this is 200. This is correct, but how to get this one? What will be the solution? What will be the solution, possible solution? So if I take 3, that will be 9. If I take 3, 4, 5. So what are the factor of 100 whose sum is 34? Factor of 100 is 24, 5. And this is 2, 2, 5. So how to get from there 34? The product should be 34. Sum should be 34. Mm, am I doing any mistake? This is symmetric matrix, that's true. Mm, mm. I think there is some problem. I think there is a problem. Just let me check this. lambda equals to, if I replace, okay, we'll look at it at the end. Okay, okay, we'll look at it at the end. So these are the problems. So let's do some other type of problems. I will do some. Okay. So before that, we'll say that when a matrix is positive definite, let let so let A be a symmetric square matrix. Obviously, so when I am writing that is symmetric, so that is square matrix, symmetric matrix where A equals to Aij, something like that. Okay, so that is here Aij is equals to Aji. Okay, because that is symmetric. Okay, so then A be a symmetric matrix, then A is said to be positive definite. Okay, so not let's start from different. Let A be a square matrix, then A is called positive definite if AXX, that can be written as the X transpose, A be a positive matrix in particular fixed in um, MNF, where F is either complex plane or real, then A is called positive positive definite if X transpose AX is greater than equals to 0 for all X, positive definite equals to 0 if for all X not equals to 0 belongs to Fn cross 1 column vector, that is column vector. Okay, so where F is either complex or real number and A is positive semi-definite if X transpose Ax is greater than equals to 0 for all X not equals to 0 in F n cross 1. So this is now if A belongs to Mn over, let's real, be a symmetric matrix, then A is positive definite if and only if it satisfies any one of the following conditions. What are the following conditions? Following conditions are all the eigenvalues are positive, values of A, you know A is symmetric, therefore all the eigenvalues of A will be real values. Okay, there is no doubt about that. And all the eigenvalues of A are positive first. Second is that all the leading principal leading principal minors of A are non-negative, I think, positive. What is the leading principal minor? This is, let's take A equals to Aij be a symmetric matrix. So don't write this one this way. A equals to A11, A12 all the way A1n, A21, A22 all the way A2n, all the way AN1, AN2, ANN. Okay, this is the matrix A. Okay, so therefore the leading principal minor is actually these are the leading principal minor. This is first leading principal minor, this is second leading, this is third leading, and this is the last leading. So therefore the leading principal minors are leading principal minors are A11, that is in general like D1, D2 is equals to A11, D1 is equals to A11, D2 equals to A11, A2. Note that for a symmetric matrix, these two terms are same. Okay, so this is the leading principal positive determinant we are talking about. Although it will go. So dn is equals to a. This is the a. dn is equals to a. So this is the leading principal minors. So if it satisfies any one of the conditions, then it will be called like this way. But for corresponding to a real symmetric matrix, we can connect a quadratic equation. Quadratic equation means 2-degree polynomial equations. Let A equals to Aij be a symmetric matrix, then Q for any then for it n by n, okay, then okay, real symmetric matrix, let Q be a real symmetric matrix. That means B real matrix, real symmetric matrix, real symmetric matrix. Then for any vector x in this Rn cross 1 column vector, Qx is equals to, let's take x is equals to x1 all the way xn, then Qx is equals to x transpose Ax, okay, is uh, is called the quadratic equation. Quadratic form is called a quadratic form of A. Conversely, if we are given a quadratic form, then we can construct a matrix A. Okay. So now, conversely, if we are given a quadratic form Qx is equals to summation of a um, summation of Aij xi xj, okay, where x is equals to that way, so it will be xi xj. So this will be all less than equals to I, less than equals to j, less than equals to n. Yes, write it at bij xi xj. That means you can look at here, whenever I and I comma j is repeating once, if I comma j is there, then j comma I is not, entry is not there, because I have taken I less than equals to j. So then there exists uh, symmetric matrix symmetric matrix A, where Aij is equals to Bij if I equals to j, otherwise Bij by 2. or bji by 2. If I less than j, uh, I less than j, yes, and if I greater than j, then that is bji by 2. Okay, so these are the things. So this will give a main point is that suppose we are giving, so for example, we are giving, suppose we are giving a quadratic from q of x is equals to ax square plus bxy plus cy square. So in that corresponding quadratic form, matrix will be, this is a quadratic form, the matrix is a b by 2 b by 2 c. This is a quadratic form. This is corresponding symmetric matrix. These things are not maybe in syllabus, but I last day, as I have said, that I will discuss. That's why I am discussing a little bit. So these are the corresponding matrix. Then a quadratic form is positive definite if and only corresponding symmetric matrix is positive definite. A quadratic form is positive definite if and only corresponding symmetric matrix is positive definite. Okay. So, but what we have seen that a positive. What is the definition of positive definiteness? So let's see the negative definiteness. What is the negative definiteness? Negative definiteness. Negative definiteness says that a symmetric matrix is symmetric matrix A is negative definite. A is negative definite if and only it satisfies any one of the following. If and only it satisfies any one of the following conditions. What are the two conditions I am giving? One is that all the eigenvalues are values of A are negative. Second, if di are the principal minor, di are leading principal minor of A, are leading principal minor of A, minus of A, then minus 1 whole to the power I di is positive. Then if this is negative, no, this is positive, minus this is positive. Then we say this is negative. And correspondingly, if we want to semi-definite, we have to make all greater than sign to equality. Here we have to, instead of negative, we have to say that non-positive. All eigenvalues will be either 0 or negative. Okay, for semi-definiteness. But the one I just want to point out is that at any cost, we should not remove the fact that A is a symmetric matrix for all these things. Okay, so let's two or three problems, and otherwise this was the problem I want to do, so that's why I came all the way. So if I want to solve this one for alpha belongs to R, A alpha is given by this way. So A alpha is given by 2 minus 1 0 minus 1 2 minus 1 0 minus 1 A. This is the matrix. So which one of the following statement is true? A alpha is positive definite for all A less than equals less than 3, positive definite for all A greater than 3, positive definite for all A greater than equals to minus 2, positive definite only for many values of A. So what are the leading principal minor of A? What are leading principal minors of A? Principal minors of A, that are, the first one is the D1 is equals to 2, that is already positive. D2 is equals to 2 minus 1 minus 1 2, that is equals to 4 minus 1, that is 3, that is positive. So D3, what is the D3? D3 is equals to determinant of the matrix A. So what is the determinant of the matrix A? That will be 2 into 2A minus 1 minus plus 1 into 1 minus 0, right? So this is so therefore it will be 4A minus 2 plus 2, that is equals to 4A. I think I have done some mistake, because note that here A is a symmetric matrix, no doubt about that. Okay, A is symmetric matrix. 2 minus 1 0 minus 1 2 minus 1 0 minus 1 8. Okay, 2 minus 1 0 minus 1 2 minus 1 0 minus 1 8. So leading principal minors, first one is 2, that's okay. Second one is 2 minus 1 minus 1 2, that is 2 to 4. 4 minus 1, that is 3, that is 0 positive. And third one is that 2 into 2A minus 1. Okay, second is minus into minus 1, this one is cancelled out. Oh, I got it. I made the mistake. Here is the mistake I made. Okay, so this is correspond to minus A. Okay, there is a 1. This one is there, minus A minus 0. So this with this minus A minus 0. So therefore it will be minus A, and that is equals to 3A minus 2. Again, am I doing any mistake? Minus of 1 2, that is A greater than 2 by 3. That's an absurd. Minus A 0, and that is, so therefore and that is greater than 0 if and only if A greater than 2 by 3, and that will hold only for this particular there. Obviously this is not there, this is not there, and this is not there, because we are getting infinitely many values. But I'm thinking whether I have made any mistake or not. If A greater than 2 by 3, then it will hold. Therefore option B is correct. Option B is only correct. Okay, so I'll do couple of problems, and this one, and this one. I'll not do any quadratic polynomial. Okay, this is an interesting problem. Okay, so this is the questions. So what is that it is asking? that it is asking that let T from R3 to R3 be a linear transformation satisfying the condition T satisfy the condition T from R3 to R3 be a linear transformation satisfying the condition T cube minus 3 T square equals to minus 2y. That implies that implies x cube minus 3x, that implies T cube minus 3t square plus 2 times identity equals to 0. That implies x cube minus 3x square plus x is equals to 0. T satisfy this equation. So this is the minimal. So if I have this one, so T satisfy the conditions. So note that. So x cube minus 3x square plus 2 equals to 0. So if I consider this polynomial, so we can look at x equals to 1 is a solution. So that I can write x minus 1, x minus 1, x minus 1. So that is x square, x cube minus x square minus 2x square plus 2x plus 2 minus 2, sorry, minus 2 minus 2x plus 2, that is equal to 0, that is equal to 0, and that says that x minus 1 x square minus 2x minus 2 is equals to 0. So what we can say that this is real, but note that for this particular thing x square minus 2x minus 2, so what is the discriminant? Discriminant is minus b plus minus root under b square, that is 4 minus 4ac, that is um, minus b plus minus root under b square minus 4ac, that is 4ac, that is 8 12 by 2, that will be 1 plus minus root 3 by 2, so that is 1 plus root 3 by 2 is a solution, 1 minus root 3 by 2 is a solution. So what are the questions here, what is the things we have, so what are the eigenvalue is equals to x equals to 1, x equals to root 3, 1 minus root 3 by 2, another is eigenvalues are I so possible eigenvalues are um, 1 comma 1 minus root 3 by 2, 1 plus root 3 by 2. So here what we can look at one thing is that if this is a this is irrational number, okay, and but t satisfy the polynomial which is satisfied by t, that is completely with coefficients are all real, rational. Okay, so if one of the root is there, so other will also be there. So they can't be there independently, they will be there simultaneously, either they both of them will be there or none of them will be there. So if one is the eigenvalue, then other has to be the eigenvalue. Okay, t satisfy this equation. So now the questions, what are the questions is here, it is said that and one is an eigenvalue, so either t, so therefore either, so either the, so either t has eigenvalue, t has only eigenvalue 1, or t has eigenvalue 1, 1 minus root 3 by 2, 1 plus root 3 by 2. So therefore, in this situation, one can get is that t has to be equals to identity. This has to be, not this has to. So this is one of the choice. Okay. So what are the option here is that, so in that situation, if so that means if one is the only eigenvalue, so x minus 1 is the corresponding minimal polynomial, is the minimal polynomial. minimal polynomial, and in this situation x square x cube minus 3x square minus 3x square plus 2 is the both minimal and characteristics polynomial. So in this situation, t is actually has to be unitarily equivalent to identity, and in this situation, t has to be diagonal. T is diagonalizable by some matrix P. So in this situation, the t has to be diagonal to this, and unitarily equivalent to this diagonal. I mean, it will be unitarily equivalent to this diagonal matrix. So therefore, diagonal with entries 1, 1 minus root 3 by 2, 1 plus root 3 by 2. So therefore, what we can say here is that in any situation, T has diagonal. So what are the options? Let's read. R3 must admit a basis B1 such that the matrix of T with respect to B1 is symmetric. That's true. At any cost, we should have this one. Okay. And second is that R3 must admit a basis B2 such that the matrix of T with respect to B2 is upper triangular. That is that is also true. That is also true. And the second one is no. Sorry, I think I made a mistake. So minimal polynomial is either already say that TB linear transformation satisfying T3 minus 2T square is equals to minus 2 times identity. Then which of the following transformation is following statement are true? R3 must admit a basis B1. Okay, main point is that so don't go this way. So I will go a little easier way. I think there is a little problematic. So what are the eigenvalue? Let's take alpha is equals to 1 plus root 3 by 2 and beta is equals to 1 minus root 3 by 2. So therefore x minus 1, x minus alpha, x minus beta, this is equals to, can be written x cube minus 3x square plus 2 equals to 0, plus 2 equals to 2. Okay, this is the thing. So what we can say here is that therefore minimal, therefore there always exists, so minimal polynomial for t are possible minimal polynomial for t are what are the, that either it can be x minus 1, or it can be x minus alpha, it can be x minus beta, it can be x minus alpha into x minus beta, it can be x minus 1 into x minus alpha, it can be x minus 1 into x minus beta, and it can be all of them. So it, in any case in any case minimal polynomial is completely factorized. Polynomial is completely factorized into linear factors and into linear factors and is product of distinct linear factors. So what we can say from here, as it is product of linear factors, so this is diagonalizable. So this fact completely factorized into linear factor, this will give triangulable. That means there exists a basis with respect to which their matrix will be triangulable, and the other is that distinct linear product of distinct, this will give that diagonalizable. So therefore, there exists a basis with respect to which the matrix T will have the matrix representation which is diagonalizable. So R3 must admit a basis B1 such that the matrix with respect to T B1 is symmetric. That we don't know. But R3 must admit a basis B2 such that the matrix of T with respect to B2 is upper triangular. That's true. Next is that R3 must admit contains a non-zero vector V such that TV equals to P. That means one is always identity, but one is always an eigenvector. But that is not true. That is not true. That means one need not be have an eigenvector. So only one option is correct here, because R3 must admit a basis B1 such that the matrix of T with respect to B1 is symmetric. That is also true, because R3 must admit a basis B1 such that the matrix of T will be diagonal, but that diagonal is symmetric, right? So R3 must admit a basis B2 such that the matrix of T with respect to B2 is diagonal, so that is upper triangular. But R3 must contains a non-zero vector V such that TV equals to V. That need not be true, because one need not be always eigenvalue, because R3 must contains two linearly independent vectors V1, V2 such that T V1 equals to V1, T V2 equals to V2. That is also false. So these two false. So let's do another problem. I think we have done this one. So what are the options? Here it is said, let A be an 3 by 3 matrix with real entries. Which of the following assertions is false? A must have a real eigenvalue. First, second is that if the determinant of A is 0, then 0 is an eigenvalue of A. A must have A be a 3 by 3 real entry. This is interesting. So we know, as A is a as A is a matrix with real 3 by 3 matrix 3 by 3 matrix entries, then characteristics polynomial must be of degree 3 with containing real entries, with containing real coefficients, with real coefficients. But a 3-degree polynomial must have an real eigenvalue. 3-degree polynomial with real entries must have a real eigenvalue. Polynomial 3-degree polynomial with real entries must have a real eigenvalue. Why this is true? Even in fact, any odd degree polynomial with real coefficient must have a real eigenvalue, because by fundamental theorem, by fundamental theorem, fundamental theorem of algebra, by fundamental theorem of algebra, if a degree 3 polynomial P has a complex root which is not real, then there must exist another root of P there must exist a root of p which is complex conjugate of the which is real. Then complex conjugate of this root will also be a then complex conjugate of this root must be a root of p. Therefore, it should have at least. Therefore, it should have at least one real root. Why this is? So let's take a degree 3 polynomial, for example, something like this. Okay, and I want to find what are the real root. I don't a b are real. I know a b are real. So my first this fundamental theorem of algebra says that if alpha plus I beta, where beta is not equal to 0, is a root of the polynomial x cube plus x square plus b uh, bx plus c equals to 0. This is full plus c equals to 0, then beta not equals to 0 implies that this is a root which is such that it is not real. Then alpha minus I beta has to be the root of this polynomial. So that means if, for example, it has to be the root of this polynomial, and third is that this is a degree 3 polynomial. So suppose we have a root which is complex. For example, let's assume this is a degree 3 polynomial. One of the root of this is complex. Let's take a root which is complex but not real. So that means if this is this one, so alpha minus I beta has to be root. But this is a degree 3 polynomial, so this has to be the another root. That either repetition or not repetition. But if it repeats one of them, it has to repeat other one again. So that means and with same repetition they will conjugate. I mean, if alpha plus I beta is a root, then alpha minus I beta is also be root, and with same repetition. Okay, that means if alpha plus I beta is repeats 2 times, then alpha minus I beta also repeats 2 times. So therefore the other root has to be real, because if that is not real and that is something like gamma plus I delta, then there must exist another root I plus delta. So in that situation we should have 4 root, but that is not possible. So that's why one of the root has to be real number. Okay, so this is very important thing. And so so now so now this is the thing. So therefore, so if a be a 3 by 3 matrix with real entries with the following statements, assertion is false. So a must have real eigenvalues. That is true. This is true. I have to find what is the false. Second is that if the determinant of A is 0, then 0 is an eigenvalue of A. That is true for always, because if a determinant is 0, that means it has to be 0 is an eigenvalue. That is also true. There is no problem about that. Because if determinant is 0, that means the characteristic polynomial will be something like x cube plus 1 plus the last term, c term, that represent determinant. So that is 0, because we know for a degree 3 polynomial or any 3 by 3, any n by n matrix, the characteristic polynomial will be x to the power n minus trace of a into x to the power n minus 1 plus whatever the last term will be minus 1 to the power n into determinant of a. So if determinant of a is 0, so this term is 0, that means up to this term every element has x, so x will be common. So therefore x equals to 0 is an eigenvalue, because that is the root of the characteristics polynomial. So that's why there must exist an eigenvector which is non-zero correspond to 0. So therefore this is also true. What is the third option says? If the determinant of a is negative, then 3 determinant of a is negative, then 3 is an eigenvalue of a, and 3 is an eigenvalue of a, then a must have 3 real eigenvalues. Okay, what is said that if the determinant of a is negative, and 3 is an eigenvalue of a, then a must have 3 real eigenvalues. That need not be true. Why that need not be true? Because let's take 3 is the eigenvalue. Let's consider other eigenvalues like minus 1 plus I into square root of, no need to be square, 2 this one, and other root is minus 1 minus I2. So So determinant of A, what is the determinant of A? Determinant of A is minus 1 plus I2 into minus 1 minus I2. Okay, just a minute. Minus 1 plus I2 minus 1 minus I2. So this product is 1 minus I square 4. So I minus I square is minus 1. So this is, huh. So this is what I just want. So no, this is again becoming plus. So therefore I have to take, no. Yeah, right. This is true. This is true. Why this is true? So let's do this. Why this is true? If if C is an eigenvalue of A, then characteristics polynomial of A is then as characteristics polynomial of A is degree 3 polynomial with real coefficient, then if other two eigenvalues are not real, then they must be of the form alpha plus I beta, alpha minus I beta. Then determinant of A is equals to 3 into alpha plus I beta mod square. That is equals to 3 into mod alpha square plus mod beta square. Because alpha plus I beta into alpha minus I beta, that means alpha square, alpha and beta real number, minus I square beta square, that is equals to beta plus beta square. So this is the thing. But this is always positive, right? So what are the questions here? It is asked that if the determinant of A is negative, but this is positive. So that contradicts to the fact that contradicts to the fact that determinant of A is negative. So therefore, this situation, what is that? When 3 is an eigenvalue and determinant of A is negative, only all the eigenvalues of all the eigenvalues of A are real number. Okay, they are real number. Okay, so this is also true. Then obviously this has to be false. But let's say why this is false. If the determinant of A is positive and 3 is an eigenvalue of A, okay, but this has to be because determinant of A is positive and 3 eigenvalues of eigenvalues consider A is equals to something like the last example, that is 3000 minus 1 plus 2y 000 minus 1 minus 2y. So note that what is the determinant. So eigenvalues are not real, that's true. 3 is an eigenvalue, that's true. And determinant of A, that is equals to 3 into 1 plus 4, that is equals to 15, that is positive, right? Because 1 plus 2i minus I square 4, so that is minus I square is minus 1 plus 4, so that is positive. So that's why this is the answer, and all other are not answer, but true, they are one faster than zero. So this is all. And I okay, so this is the last class, this is also the last tutorial. So thank you for Okay, so I'll request everyone who is watching this video when it will uploaded in the particular section where it has to be. So I request everyone, please fill the feedback form, and if you have any problem, you can ask. I will try to give answer before your exam. But, okay, thank you. So I'll stop here.